again for the second video of the series. As I said, it's a series of videos on electrostatic. The second video will be basically on electric flux. So we'll be starting with some basic concepts, and then we'll go to the definition of electric flux, and then establish the Gauss law. So the first thing that we must know is that whether area is a vector. The simple answer is no. See, area is always being an scalar. We cannot put it as vector, but for mathematical convenience or whatever be the thing, we can make it as a vector. And the way is also very simple. The way is that we put some, suppose we have a surface or some area, we take some unit vector which is directed outward and also normal to the surface. So you can see here that we drew an outward unit normal vector to it and represent the direction of it as the direction of the area. So simple thing is that the area is not a vector, but we can make it vector. The way is that we put some unit vector which is outward, going out. Suppose this is the board and the direction of the vector will be like this, not like this. So it will be coming outward and also normal to the surface. That means I'm making 90-degree angle with the surface. So that's what we can make, the way how we can make it a vector. So area is now a vector. So we can pictorially show it here. Again, figure 1.1. Here S is a surface, is an area, and we draw a normal vector here, n cap. It's normal vector, unit vector, and we see now that S is no longer a scalar now. It's become a vector. S vector is equal to S n cap. So n cap is representing the direction of area S. Similarly, if usually the area can be in a maybe some continuous distribution of things may be there within a surface. To that end, we usually divide the surface into some small elements, and suppose this is ds being a very small element out of S, and that's in the same way that ds has a unit outer normal vector n cap, and such that the ds is also now becoming a vector. Ds vector is equal to ds n cap. So wherever we can take a big surface or a small surface, the way is same. We just put a unit vector outward and normal in direction, and then that unit normal direction, direction of that unit normal vector, make it the direction of the area. So coming back to then electric lines of force, before defining flux, we must know what is electric lines of force. Actually, what we do is that we want to represent electric field at some different points of space, and to do that, we do some pictorial representation, and that pictorial representation is nothing but that electric lines of force. So the definition is that it is the part which may be straight or may be curved in the electric field, and such that the tangent to it gives us the direction of the electric field. Suppose I'm drawing some curve, suppose, and that if I choose a point on the curve and draw a tangent on that point, that tangent will represent the direction of the electric field at that point. So this is the definition. So an electric line of force may be straight or may be curved line. Important point is that if we draw a tangent at any point, that tangent will represent the electric field or the direction of the electric field. Then some of its properties are there. You already come across these things, that they never intersect. Two electric lines of force never intersect each other. The second one is that they start from the positive charge, coming out of the positive charge and enters in the negative charges, and they are always normal to the surface. If you take a surface, the electric lines of force are normal to the surface. So these are some properties. So more properties you can go back to your 10 plus 2 course as well. So we have depicted some of important charge distributions, the lines of force for some important charge distribution. The first one is positive charge. For positive charge, you see that the lines of forces are coming outward. The direction of the arrow mark is outward. So positive charge, the electric lines of force are coming outward. This is radially outward, so the distribution is like spherical distribution. For negative charge, this is same, but only thing is that they enters into the negative charges. And this is an electric dipole, plus Q and minus Q. The charge, the lines of forces are coming out of plus Q charges, and it is entering in the negative Q charges, minus Q charges. So these are some another lines where they are starting from plus Q and going back to they're starting from plus Q and then entering at minus Q. These are some two equal charges, plus Q, both are same charges, like charges, plus Q, and for these two positive equal and positive charges, the lines of forces are like this. And here, another distribution, another charge distribution, figure number E, we have two charges, Q1 and Q2, where Q1 is greater than Q2, and we see that lines of forces are more in Q1. That means if the magnitude of the charge is more, the lines of force, number of lines of force will be more. So this is Q1 and this is Q2, and we can see that the lines of forces coming out of Q1 is this, and this is the lines of forces coming out of Q2, and they're repelling. That's why that lines of forces are actually repelling each other. And this figure number F, we have put a charge plus twice Q and another charge minus Q. Both charges are unlike now. One is positive charge, one is negative charge, and their magnitudes are also not same. In that sense, we can see now from the positive charge, the electric lines of forces are coming outward, and they are entering at the negative charges. And we can see here that the number of lines of forces are here smaller as compared to this. This is because plus twice Q is more in magnitude than minus Q. So important thing is that electric lines of forces come out of positive charges, it enters the negative charges, and more the magnitude of the charge, more the number of lines of forces. So we can have some more such kind of distribution at our home also. We can try for that. Then let's go for the definition of electric flux. And as usual, the electric flux can be defined in two ways, qualitative as well as quantitative. What is qualitative definition? The number of lines of forces, electric lines of forces, passing normally through a surface. So we take a surface here. How many number of lines of forces are passing through this surface? Normally. So that's the number of lines of forces is the electric flux. This is the qualitative definition. But we usually encounter with a quantitative definition, and it is defined like this. F is the flux here, and it is defined as dot product of electric field and the area vector. It's a vector, dot product of electric field and vector. And we represent like this, E and this S, and then ultimately ES cos theta. We will coming back to the figure, because A dot B is equal to E AB cos theta, so like the ES cos theta. This is definition of scalar. And for a small area, suppose corresponding to figure 1.3b, we're coming back to that. We have the flux dF, the small, since we are choosing a small area ds, so flux is also dF, and in that case E dot. In the same way we are defining this, E ds cos theta. So we can coming back to this thing. For this, the flux is E dot n cap S. That means E dot S vector. E vector dot S vector for this surface. And within this surface, if we take a small area ds, then the flux will be E vector dot ds vector, or E vector dot n cap ds. So which already we have defined, and this was the result. This is for figure 1.3, and this is for figure 1.2. The question is that corresponding to this figure, what will be the total flux? The answer is very easy. We have already defined the flux for the surface. What we do is that since the charges are continuously distributed, we will take integration over the whole surface, and it is done like this. So the flux for the whole surface in figure 1.3 is, we just integrate this expression and you get like this. So thing is that quantitative definition is that you take the electric field vector and dot product of electric field vector and the area vector. And within a big surface, if there is a small surface, we can find also the flux for them. The same definition is applicable. And when we talk about the flux for a whole surface, then we take just the integration of that small amount of flux through the small surface element dx. So with this definition of electric flux both in qualitative and quantitative, so this video is ending here. I hope that you enjoyed the video. Our next video will be on Gauss law. You can get a more idea about electric flux and applications as well. Thank you very much for watching.